Welcome to the debate. Our focus today is on some really interesting recent advancements in video-based collision prediction models. Specifically, we're looking at the introduction of BADAS and its, its central and pretty provocative claim, the necessity of shifting to an ego-centric problem formulation for advanced driver assistance systems, or ADAS. This work effectively argues that a core conceptual flaw in previous datasets, basically training models on irrelevant accidents, was the main roadblock for reliable real-world deployment.
Yeah, the paper certainly presents some compelling quantitative evidence, impressive state-of-the-art performance by BADAS, no doubt. But I think the core intellectual tension we really need to explore here is whether this breakthrough is fundamentally a conceptual victory, driven by this rigorous redefinition of what collision prediction actually means for an ADAS system, or if the performance gains, impressive as they are, ultimately are owed more to the successful integration of these very sophisticated, heavy-duty foundational models and, frankly, massive proprietary data scale.
Which factor is truly more decisive for achieving reliable real-world collision prediction? Is it the methodological rigor of the egocentric data reformulation and the standardized labeling? Or is it more about the brute technical power that's supplied by the VJPA2 foundation model, fine-tuned on these unprecedented volumes of real-world data?
Right, and I'll be arguing that the architectural choice, specifically that VJPA2 backbone, which, we can think of as a state-of-the-art video understanding foundation model, really optimized for temporal reasoning, and just the sheer data scaling provide the necessary predictive power that previous, simpler methods fundamentally lacked. It doesn't matter quite as much how clean the input data was. Performance comes from capacity.
And I'm going to argue that the methodological reformulation, that critical shift to an egocentric focus, and the standardization of those temporal labels is the absolute non-negotiable prerequisite. It defines the goal, you see. The architecture merely provides the means to reach it. Without that conceptual clarity, all that architectural power is just completely wasted, detecting irrelevant events, leading to a system that users would, frankly, immediately reject. Okay, so let's first establish the primacy, as I see it, of this conceptual reformulation. The core challenge BADAS addresses is, well, as the authors clearly put it, the fundamental misalignment between training data and actual driving scenarios. Now, if we look back at the legacy benchmarks that really dominated the field for a while, datasets like DAD and DoTA, this misalignment was staggering.
Okay.
Consider DAD, which was, a benchmark standard for some time. It contained 92.0% non-ego accidents among its positive samples. 92%. And the DATA 2000 dataset, a later iteration, still had over 40% non-ego accidents. Now, to translate this highly academic figure into practical ADAS terms, that means we were essentially training collision prediction systems to detect and potentially alert the driver to accidents happening, say, in the next lane, 50 yards away, or maybe way down the road, accidents that required absolutely zero intervention from our car. Training a model on that kind of noise essentially forces it to generate excessive false alarms in real deployment. It turns the ADAS system into the electronic equivalent of, the boy who cried wolf.
I agree that the false alert problem is absolutely critical, both for user acceptance and for regulatory compliance in ADAS. You just cannot deploy a system that constantly screams warnings about irrelevant events. People would turn it off.
Exactly. So BADAS's strength, therefore, lies not merely in filtering out irrelevant videos, but in its whole egocentric reformulation. It rigorously mandates that training focuses only on scenarios where the ego vehicle either experiences a collision or executes an emergency maneuver. And it treats near collisions, those critical saved events, as positive examples too. This is fundamentally about relevance, and crucially, this conceptual clarity extended to the necessary re-annotation protocols. They used I believe it was 10 annotator consensus method for defining the standardized alert timing, the T alert. Now, this consensus finally addresses the pervasive subjective definitions that plagued previous benchmarks. where alert time was often defined really vaguely, like abnormal behavior onset or just inevitability. This methodological rigor, it validates the training signal by ensuring the temporal labels are standardized and actually applicable to human reaction times.
Okay, I acknowledge that the ego-centric filtering and the consensus labeling are essential for creating a dataset where performance can actually translate into practical, low false alarm deployment. I don't dispute the necessity, but I want to reiterate that necessity doesn't, in my view, explain the sheer quantitative leap observed across the standard academic metrics. I still maintain the defining technical success here is the first application of this VJ-P2 foundation model backbone, combined with the successful management of large-volume, high-quality data.
That quantitative leap is staggering, I grant you. But how much of that performance do you really think is inherent to the VJ-P2's complex structure versus, say, how that structure was simply better leveraged by the new clean data?
Well, I weigh architecture so heavily because the quantitative improvement across standard academic metrics, average precision or AP, and area under curve or AUC, is just simply too dramatic to be explained by cleaning the data set alone. AP, just for the audience, measures how well the model avoids false positives relative to its true positives across all confidence thresholds, to measure of raw discrimination power. And look at the figures. BADAS 1.0 achieves 0.94 AP on the revised dataset. Now, compare that, it's devastatingly better than older academic baselines like DSTA or Ustring, which hovered around 0.06 AP. And even the established industrial forward collision warning, the FCW ADAS baseline, was only at 0.11 AP. That kind of performance gap represents an unprecedented ability to extract complex predictive signals from video frames, which to me is the hallmark of a powerful foundation model.
But that comparison is only really valid after the re-annotation has occurred, right? After it created a relevant testbed in the first place.
Indeed. True. But even when comparing the architectural components against each other within the study, the ablation studies, I think, confirm my point. The authors meticulously tested what provided the gain, fine-tuning the VJ-P2 base, meaning they fully adapted the large pre-trained video foundation model, provided the single largest gain. It jumped the AP from 0.707 to 0.928 over merely freezing the base model and training only the small prediction head. This demonstrates pretty clearly that the foundation model's vast capacity and its inherent temporal understanding are what generated the signal, not just the cleaner labels being applied on top of some simpler architecture.
Okay, that distinction you drew between possibility and utility leads us right into the core debate on metrics. Let's start with this tension between realism, measured by mean time to accident or MTTA, and that raw predictive power we see in AP and AUC. I'd argue that the ego-centric framing delivers realistic performance, which is just paramount for ADAS systems. Existing baseline methods, remember, trained on that noisy data, reported physically implausible MTTA like 9 to 10 seconds before collision on test sets like Nexar. This isn't useful. It's clearly an artifact of the model reacting to distant, irrelevant, non-ego events way too early. BADAS models, by focusing strictly on the ego vehicle, consistently maintain these realistic prediction windows of about 3 to 5 seconds. Now, this aligns perfectly with the known human median reaction time around 1.70 seconds before impact, providing an alert window that is actionable. The primary purpose of collision prediction in ADAS has to be reliability and human utility, which is achieved by optimizing for reduced false alerts and realistic timing. And both of those are enabled precisely by the ego-centric filtering and that standardized T-alert.
Okay, I agree user acceptance is tied to low false alarms, and yes, the methodological changes definitely fix the unusable MTTA problem. But I'm not convinced that the realism is the primary technical achievement here. AP and AUC, as measures of ranking quality, tell us that the model can truly discriminate between a collision trajectory and a safe maneuver with high confidence. That massive increase in AP on Nexar, for instance, jumping from 0.53 to 0.86 AP, that's a clear signature of a technically superior model. The realistic MTTA alignment is, in my view, a welcome and necessary consequence of VJEPA2 applying its superior temporal reasoning capabilities to cleaner consensus-annotated labels. Cleaning the data makes the output useful, I grant you, but the VJEPA2 architecture makes the high-confidence discriminative output possible in the first place.
That's an interesting perspective, though. I might frame it slightly differently. I believe the older baselines weren't necessarily architecturally incapable of finding collision signals. They were conceptually burdened by the flawed training task itself. If you task even a powerful model with detecting all visually salient accidents, well, it's going to deploy its power inefficiently, right? It'll alert to distant, irrelevant accidents too early and inflate the MTTA. By providing the clean, ego-centric signal, VJPA2 model to focus its sophisticated architecture on the relevant physical process unfolding within that crucial 3-5-second window, which naturally leads to a realistic TTA. The methodology acts as the essential filter that directs the architectural power effectively.
Okay, let's maybe move our discussion then to the continuous nature of the data scaling effect versus the sort of discrete act of data cleaning. Figure 6 in the paper shows a pretty definitive performance curve. It reveals a continuous, logarithmic improvement in validation AP as the training data scales substantially, going from 1.5K videos in the open variant, BADAS-Open, up to 40,000 proprietary videos in BADAS 1.0. This demonstrates pretty clearly that the potential of data scaling is far from saturated, and that high-volume proprietary data is fundamentally key for superior edge case handling. The ultimate real-world performance, BADAS 1.0 superior overall score, that 0.94 AP on DAD versus 0.66 AP for the open variant, is strong proof, I think, that volume, when leveraged by a high-capacity foundation model, drives the ultimate success.
I see why you think that. And look, there's no doubt that 40,000 videos of clean, relevant data is superior to 1,500. Of course it is. However, let me offer a different perspective. That scaling effect, impressive as it looks on the graph, would have been largely meaningless if those 40,000 videos were polluted with 40 to 92% non-ego events, as we discussed was the standard for legacy datasets. And the ego-centric filtering, that was the absolutely necessary precursor to create a valid training set upon which scaling could even have a meaningful effect. Scaling clean, high-signal data is effective. Scaling noisy data just scales the noise and, consequently, the rate of false alarms. Furthermore, the public release of the re-annotations for DAD, DoTA, and Data 2000 is itself a major methodological contribution. It provides the definitive ground rules for all future collision research in this area, regardless of which foundation model happens to be used next. It sets the empirical standard moving forward.
I agree that the groundwork was essential, foundational even, but we must acknowledge that only a model with the massive capacity of BJPA2 can fully exploit that large, clean dataset. A simpler, smaller model might quickly saturate its learning potential, or maybe just overfit to the smaller 1.5K set. The architectural depth of the foundation model is really the engine that converts 40,000 clean videos into that continuous, massive performance jump we see in the scaling curve.
But that capacity, however powerful, still faces inherent limitations, which brings us neatly to the long-tail distribution challenge. The detailed analysis of long-tail performance in Figure 9, well, it clearly shows a significant deterioration in recall for vulnerable road users, pedestrians, cyclists, motorcyclists, and also animals. The recall on pedestrians, for example, drops noticeably compared to vehicles. Now, this degradation occurs despite the VJP2 architecture and the 40,000 training sequences. This points, I think, quite strongly to the inherent limitations of relying solely on data distribution and architectural power to solve the critical problem of rare, visually ambiguous, safety-critical events.
That's a compelling argument, and it certainly highlights a current weakness. But have you considered that this degradation precisely underscores the technical challenge? Filtering for ego-centric events, as we've discussed, solves the relevance problem. It gives us useful alarms. But it doesn't solve the diversity problem, the long-tail distribution. The failure here isn't really a failure of methodology, is it? It's more a failure of data acquisition and the model's capacity to generalize from rare instances.
The solution, arguably, requires even more data scale, or perhaps specialized architectural strategies, which, by the way, foundation models are kind of designed to incorporate, to robustly generalize across these visually diverse, low-frequency event types. The challenge remains fundamentally one of model capacity and data volume to handle the sheer visual complexity and kinetic variation of the real world. And that's exactly where advanced architectures like VJ-P2 are needed to push performance further than simpler models ever could.
Perhaps that if the initial methodological framework hadn't been rigorous enough to mandate explicit evaluation of these safety-critical rare events by actually segmenting them in the test set, then that long-tail failure might have just been obscured, averaged out. The conceptual framework defines the problem space, it dictates the necessary performance targets, and critically, it exposes where the architectural solution must go next to truly solve ADAS safety. It's the compass, even if VJPA2 is the engine driving us there. Okay, so to summarize my position, we've established, I think, that the BADAS project provides a crucial lesson. Effective collision prediction for practical ADAS begins with rigorous problem reformulation. By redefining the task as ego-centric and standardizing those temporal annotations via consensus, BADAS created the clean, high-signal environment necessary for any subsequent algorithmic advances to actually be effective in the real world. It prioritized reliability and realistic alert timing. It fixed the conceptual flaw that held the field back.
And while we strongly agree on the high quality and the absolute necessity of that methodological framework, I maintain that the state-of-the-art performance, that sheer leap in AP and AUC metrics we see across diverse benchmarks, is fundamentally a product of harnessing the architectural power of the VJ-PET2 backbone. The study clearly demonstrated the continuous, non-saturated gains delivered by increasing proprietary data scale-up to 40,000 videos. This proves, I believe, that technical capacity and sheer data volume are necessary components to achieve true discriminative power and robustness, especially in novel scenarios.
It seems we agree then that the transition from flawed academic datasets to a truly deployable ADAS solution required a kind of synchronized leap. The conceptual clarity provided by the ego-centric formulation, definitely, coupled with the computational capacity that's really only available through these state-of-the-art video foundation models.
Indeed, the findings ultimately demonstrate the very tight coupling between data methodology, that critical shift to an ego-centric focus, and architectural complexity, the robust application of VJ-P2. Both were essential, it seems, for bridging the gap between current advanced driver assistance systems and the very ambitious goal of fully autonomous driving safety.
You know that feeling, right? You're driving along and suddenly your car screams at you with a heart-stopping beep for nothing. It feels like your car's safety AI is just crying wolf. So what's the deal? How do we build a system that's actually smart about safety and, a little less paranoid?
Yeah, it's a great question. And the first thing you might think is, well, we just need a bigger, smarter AI brain, right? But what if I told you the problem isn't the AI's IQ at all? What if it's the textbook we've been giving it to study? Okay, let's get into it.
Because look, this goes way beyond just a few annoying beeps. The research we're digging into today sees this whole false alarm problem as a massive roadblock. Every time your car yells at you for no reason, you trust it a little bit less. And that makes these potentially life-saving systems kind of useless in the real world. So where does all this paranoia actually come from?
And this, right here, is the absolute core of this entire paper. The problem isn't the algorithm. It's not that the AI isn't smart enough. It's the data. It's the textbook. The data sets we've been using to train these models have a huge, fundamental flaw that basically teaches the AI to focus on all the wrong things.
To really get this, we have to understand one key term, an ego-centric collision. Now, it sounds a little technical, but all it means is an accident that is a direct threat to your car, what the researchers call the ego vehicle.
It's about separating the accidents that are your problem from some random fender bender your camera just happens to see nearby. Here's a simple way to think about it. A general collision is like a security guard sounding the alarm because there's a commotion happening way across the street. Yeah, it's an event, but it's not a direct threat to you. An ego-centric collision? That's the same guard yelling because someone is literally trying to kick down your front door. Right now, most systems are like that first guard. They see everything, so they yell about everything. So just how bad is this data problem? Well, the researchers went back and reanalyzed the big data sets used to train these AIs, and wow, the numbers are just wild. In the data You know that feeling, it's the street. Okay, so that's the theory. A better textbook and a smarter student. But does it actually work in practice? Well, the researchers put BADAS head-to-head with all the other top models, using these newly cleaned up ego-centric data sets. Let's see what happened. And wow, this chart pretty much says it all. We're looking at prediction accuracy here, and that purple bar representing BADAS, it's just towering over the competition, especially on that DAD dataset, the one that was 92% junk. The older models were basically useless. This isn't just a little bit better, this is a massive leap forward, and it all comes from simply focusing on the right problem. And you can literally see what that performance looks like here. The blue and green lines are the older models. See how their collision scores are just all over the place, jumping up and down erratically? That's what causes all those false alarms. Now look at the red line, BADAS. It's this clean, stable, confident signal that rises decisively only when a collision is about to happen. Now that is a system you can actually trust. Let's walk through what this looks like in a real scenario. So, the car's driving through a tricky intersection. BADAS is just chilling in normal mode, everything's green. But as the situation starts to get sketchy, it correctly bumps up to caution, orange. And then only when that collision is truly unavoidable does it issue the take action red alert. It's intelligent, it gets the context, and crucially, it's timely. And that word, timely, is so important. Because as the paper points out, it's not just if a model predicts a crash, but when it predicts it. An alert that comes 7 seconds too early isn't a better prediction. Functionally, it's just another false alarm because it's not actionable yet. This chart really drives that point home. See that green box on the far left? That's when human experts agree an alert should happen, about 1.7 seconds before impact. Now look how closely BADAS aligns with that. It's almost perfectly in sync with human judgment. Now compare that to the other models, which are alerting people more than 6 or 7 seconds too early. They're just crying wolf. So the really crucial point here is that this is about so much more than just making our cars less annoying. This whole ego-centric approach has huge implications for the future of car safety, for building trust between people and AI, and even for the entire path to fully self-driving cars. And one of the most promising things they discovered is that this approach scales beautifully. As the researchers fed the model more and more high-quality, ego-centric data, going from 1,500 videos all the way up to 40,000, the accuracy just kept on climbing. This proves that with more real-world, relevant data, these systems are only going to get better. And that really gets to the heart of why this all matters. At the end of the day, a system that is accurate, reliable, and well-timed is a system we will actually learn to trust. And that trust is the absolute foundation that all future driver assistance systems and autonomous vehicles have to be built on. But the work isn't done. While BADAS is absolutely state-of-the-art for common car-on-car collisions, the paper is very upfront about its limitations. Its performance takes a hit when it comes to what are called long-tail events. You know, the rare but supercritical scenarios involving pedestrians, cyclists, or animals, which just weren't as common in the training data. And that brings us to the final, provocative question. This research has given us an incredible new playbook for teaching an AI to predict common crashes with stunning accuracy. But the next great challenge, the next frontier, is figuring out how we teach it to master the chaos of the real world, the rare, the unexpected, and that long tail of everything that can possibly go wrong on the road.